Hi, I am Jahidul Islam Laku, presenting the intro and historical perspective of extended finite element method as part of EME 521 project. So the first question is, what is XFEM? It's basically a numerical method uh, that is an enhancement of the standard finite element method. It is based on generalized finite element method and partition of unity method. It was initially developed by Ted Belichko along with other collaborators to overcome the shortcomings of finite element. Since then, this method is widely used to solve problems involving discontinuities, material interfaces, and singularities. As the core idea of XFEM is taken from FEM, we must know the working principle of FEM. FEM actually solves problem by discretizing a domain in a space into smaller parts. These smaller parts are often called finite elements, like the shaded portion in the figure. Each finite element have finite number of nodes that can be connected with each other and also with the nodes of the other elements to form a mesh. Each element follows the governing equations and solving the equations formed by all the elements give the solution of a particular problem. However, XFEM has some shortcomings. Constructing the mesh of a domain with defects, cracks, voids are expensive. For instance, a structured mesh must be aligned with the cracks or voids, which can be very complicated. Because meshing around complex geometry of voids and cracks is complicated and error-prone, this method often becomes costly. Here comes the XFEM. The advantage of XFEM is meshing is independent of discontinuity. This is achieved using the technique nodal enrichment. Nodal enrichment allows to enhance the approximation space using a support node, basis function, and local approximation function. Here, phi ai is the basis function at node I, and LAI is the local approximation function at node I. And finally, phi A is the final approximation. There are multiple functions for local enrichment, for example, Heaviside function, jump function, crack tip function, etc. In the figure, you can see at the crack tip, the crack tip function is used for local enrichment. Now, if we look back to the historical perspective of XFEM, the first major work was done in April 1999. It introduced XFEM using enrichment functions to model crack, utilized the Heaviside and crack tip asymptotic functions. It requires minimal remeshing. Arbitrary alignment of the crack within the mesh is allowed. It is cost effective compared to FEM. And in July 1999, it introduced the concept of enrichment functions within FEM to represent crack without mesh refinement. It used continuous enrichment near crack tip functions. It combines the continuous Haar function and near tip asymptotic functions through partition of unity method. It allows the prediction of crack propagation by adding new crack segments and redefining the crack tip location. In 2000, it introduced 2D asymptotic crack tip displacement fields into FEM using partition of unity concept. It enabled modeling of crack domains without explicit meshing of crack surfaces. It provides computation of stress intensity factor for planar 3D cracks. Another major work of 2000 is it presents the XFEM for modeling cracks with multiple branches, multiple holes, and cracks initiated from holes. Mesh-independent representation of cracks and holes. It showed enriched approximation based on interaction of discontinuous geometries within the mesh. Another key work of 2003, it introduced enhanced strain formulation for XFEM, focused on blending enriched elements with standard finite elements, addressed transition zone to improve numerical stability and accuracy. Another major work of 2006 developed a mesh-based enrichment strategy using moving least square function near discontinuities and standard finite element shape functions elsewhere, introduced one shape per node that encodes non-solutions characteristics, utilized mesh-based weight functions for flexible enrichment. And in 2007, XFEM is applied to fatigue crack problems such as 3D fatigue crack propagation, 2D elastic plastic fatigue with closure effect, rolling contact fatigue, and dynamic crack growth simulations. And this final work of 2010 introduced XFEM and level set coupling for nanostructures. It tackled mechanical effects due to surface and interface discontinuities, addressed strain and displacement discontinuities in nanoscale, and included surface energy stress elasticity in the model. So that's all from my side. Thank you.
Hi, this is Steve, and this is the part of the XFEM principles. We mentioned it. I do some slides on it about the fundamental principles and the unity method and the enrichment concept here. The fundamental of XFEM lies in the partition of unity method proposed by Babaskar and Malank in 1997. This method allows us to add enrichment functions locally when maintaining global continuity in our solution. Mathematically, this is expressed as the sum of our shape functions equaling 1 and at all points in the domain. And the core innovation of XFEM introduced by Balesco and Blank in 1999 is the enrichment concept, which allows us to model this continuous independently of the mesh. And next part, let's look at how XFEM builds upon standard FEM approximation. In the standard FEM, we have this formula expression where the displacement field is approximated as the sum of shape functions multiplied by nodal displacement. XFEM extends this by adding an enrichment term. This term consists of the same shape functions multiplied by enrichment functions and additional degrees of freedom. This structure is powerful and because it allows us to incorporate known features of the solution like discontinuities or singularities, and which can directly into our approximation space. And just like the shape functions, NIX are the standard FEM shape functions. UI represents our standard nodal degrees of freedom. 5x represents our enrichment functions that capture the special features of the solution, and the AI represents the additional enriched degrees of freedom that determine the aptitude of these special features. And then, which is about the two key aspects of the formulation, as they are element partitioning and blending elements. For elements cut by discontinuities, like cracks, we need special integration techniques. It's proposed by Balletes Kiko in 2021. These elements are partitioned into subdomains as shown in this diagram. Integration is then performed separately in each subdomain to accurately capture the discontinuous behavior. Notice how the elements on the right shows diagonal line representing a crack or discontinuity with pattern nodes used to facilitate the integration. Equally important are blending elements, which provide a smooth transition between fully enriched elements and the standard elements. This maintains continuity across the entire domain and ensures that our enrichment is properly located to where it's needed. So just like this shown, so this is the part of the principles of XFEM.
I will presenting the governing equation of the extended finite element method, particularly in the context of linear fracture mechanics. We begin by considering a crack domain where discontinuities, such as cracks, are presented implicitly without the need to remesh the geometry. This is one of the key advantages of XFEM. We consider a 2D domain omega crossed by the discontinuity gamma sub d. The governing equation starts with the strong form of the equilibrium equation. Del dot sigma plus b equals 0. The boundary conditions include u equals u bar on gamma sub u. Sigma dot n sub gamma equals t bar on gamma sub t. Sigma dot n sub gamma sub d equals 0. In order to model the discontinuity of crank interface in the XFEM, the nodal points of elements cut by the discontinuity are enhanced using the enrichment function sin x. The enrichment of displacement field, you can see this shape. The nx denotes the standard shape function. The enhanced shape function can be divided into standard and enriched path. The choice of enrichment function sin x is dependent on the position of discontinuity in the domain. Generally, there are two types of enrichment function used for the correct body in this problem: the Heaviside jumping function and the asymptotic crank tip function. Finally, the XFE approximation of the displacement field is shown in this equation. The first term is the standard FEM. The second uses the Heaviside jump function for modeling displacement discontinuities across cranks, and the third uses asymptotic crank tip functions to model singularities near crank tips. Accordingly, the string vector corresponding to the approximate displacement field we apply the Galerkin method to derive the weak form by multiplying the equilibrium equation with a test function delta u and integrating. Applying the divergence theorem, imposing the natural boundary condition, and satisfying the traction-free boundary condition on the discontinuity surface, the integral equation you can see in this form. It must be noted that the second integral in the left-hand side of equation on the discontinuity gamma sub d can be eliminated from the integral equation, assigning the positive and negative sides to gamma sub d and imposing the traction-free boundary condition on the crank face. So the earlier equation is shown that, and we can expand it to this form. The K is the global stiffness matrix. The U included standard and enriched nodal displacements. The F is phase force vector. Each submatrix corresponds to coupling between standard, Heaviside, and crank tip. The force vector is also divided accordingly. Each component included body phase and traction contributions computed over the domain and boundaries. Finally, we compute the special derivatives of enriched shape functions, and like this shape can be simplified in this shape. These expressions are very crucial for assembling enriched stiffness matrix.
My name is Lillian, and I'm going to be walking you through the XFEM hand calculation. For this calculation, we're going to be looking at a 1D bore with a fixed end and then a strong discontinuity or a crack in the middle. The full length of the bar is 3L. The discontinuity is located at 1.5L. And then I've got a list of parameters that we'll be using throughout this calculation, including E representing Young's elastic modulus, A being the bar's cross-sectional area, omega being the individual elements, X being individual nodes, F being the external forcing factor, U being the displacement, A being the enriched degrees of freedom for nodes that are closest to the discontinuity, H being the Heaviside function, which I'll talk about more in a second, and then Ni and Nj being the shape functions. The goal of this calculation is to solve for K, the stiffness matrix, at each element, and then the combined stiffness matrix, and then to solve for U at each node. To start us off, I'm going to go over a couple guiding equations and then give you a little bit of a more detailed background of how we're setting up this problem. So there will be 4 nodes in total. There are 2 standard nodes. Node 1 and node 4 are standard nodes that have 1 degree of freedom each. And then there are 2 enriched nodes, nodes 2 and nodes 3, which have 2 degrees of freedom for each. Nodes 2 and 3 are enriched nodes due to their proximity to the discontinuity. And then there are the 3 elements. So element 1 is a blending element and element 3 is a blending element. But element 2 is an enriched element, meaning that it contains that discontinuity. So some equations that we'll be using to go through this are the shape function equations seen here. And then we'll talk about the enrichment function that has both the standard FEM and an enriched term in it. That gives us the XFEM calculation that we're looking for in this example. We'll be using a Heaviside function where h of x will be positive 1 when x is less than 1.5L, so before the crack function here, or the discontinuity here. And then h of x will be negative 1, where x is larger than 1.5L, so beyond the discontinuity. And then again, the goal of this is to solve for the stiffness matrix, which is represented as K. K has 4 components, KUU, KUQ, KUQ transpose, and KQQ. These are all defined in these equations down here that include the strain function and the material constitutive matrix, which we derive from the stress and strain of the system. We'll use each of these to solve each of the 4 components of this matrix. So KUU is just the standard FEM portions of our analysis. KQQ is just the enriched portions of the analysis, and KUQ and KUQ transpose are a combined of both the standard and the enriched portions of the analysis. So walking through our setup a little bit more. So we've got our 4 nodes here, which I've explained already. And we need to determine the different displacement vectors at each node. That's part of what we're solving for. We know that at node 1, that it's fixed, so it won't move. And we know that node 4 experiences some displacement that we represent as U. So we really need to solve for U2 and U3. The degree of freedom here are represented by Q2 and Q3. That's because these enriched nodes have those 2 degrees of freedom for each. Again, so node 1 is located at 0, node 2 is located at L, our discontinuity or crack is located at 1.5L, node 3 is located at 2L, and node 4 is located at 3L. So as we go through at each node. Each of these nodes follows a linear standard shape function, with node 1 being orange here, node 2 being green, node 3 being blue, and node 4 being purple. And again, for our Heaviside function, for Heaviside function, we'll be going from 1 to -1, being at 1 when the location is less than the discontinuity, so 1.5 L, and then at -1 after the discontinuity, so greater than 1.5 L. For our enriched function, or for our enriched shape function, we're looking at how this can provide continuity across our enriched element here for element 2. So here we're looking at element 1. At this element, we're using the Heaviside value of 1 because L is less than 1.5 L, which is where our discontinuity is. And we can see that here we're going from 0 to L right here. We have one standard node and then one enriched node. And then defining our shape functions and our strain matrices are right up here. So we have our standard shape function as being 1 minus x over L and XL, and our enriched shape function as h times x over L, which we can represent here because h is 1 as just x over L. Our strain matrix here for the standard portion of this element is 1 over L times the matrix -1 by 1. And then the enriched portion of our strain matrix is h times 1 over L, which again, because h is 1 in this, for this element, we get 1 over L. So plugging those values into our K matrix, into the 4 components, again, KUU has 2 standard components, KUQ has a standard component and then the enriched component, KUQ transpose has a enriched component and a standard component, and then KQQ has both enriched components. So pulling out those constants in the integrals here and then integrating, we get a simplified equation here for K of element 1 as AE over L, and then this matrix defined here. So we're going to jump to element 3 because it is very similar to element 1. The biggest difference here is that we have the Heaviside function as equal to -1 because we're past our discontinuity here, and L is greater than 1.5 L. So again, we've got our defined shape functions and strain matrices up here. Again, plug those into our K matrix down here for each component. Pulling out our constants and integrating, we get the same simplified equation that we did for equation or for element 1. But again, the biggest difference here is that we're using the H is -1 since we're on the far side of our discontinuity. So element 2 here, we're jumping back. This is a little more complicated because it has our discontinuity in the middle and we're dealing with 2 enriched nodes here. So nodes 2 and 3. So for the left, we need to treat this as it is before the discontinuity. So H here will be 1. So this will use all of the same parameters that we had for our element 1. And calculate out to be a very similar matrix. But we need to calculate each individual component of K separately. So by doing that, we're looking at, and by here left, I just mean H equals 1. So we're looking at KUQ left here, and that gets us this matrix here. And then doing KQQ left here, which gives us the same matrix down here. In order to get the full picture, we need to do both the right and the left side for this element. So the right side follows the same properties, just using h equals 1 or -1 here because we're on the far side of the discontinuity on this side. So again, plugging the same parameters that we had for element 3 for our shape function and strain matrices. Up here, we plug those into our k components to get k right UQ as this matrix. It differs from the left component by just having different placements of the negative sign. And then we get the KQQ for the right side here, which is the same as it was for the left side. So in order to get the full K for element 2, we need to combine KUQ for both sides. That gives us a matrix shown here as EA over 2L and then a 2 by 2 matrix of 0. So for KUQ or KQU, we know that that's just KUQ transposed. So that'll give us the same matrix of zeros. And then KUU will be the same as what we've gotten before. It's because this doesn't have the enriched values in it. And then for KQQ, again, we have to combine the two matrices together, and that combination results in this matrix over here of EA over L, 1, -1, -1, 1. So combining all of those components here, we get the full K matrix for our element 2 represented here. And then for our final solution, so we need to combine all of their K elements to get our stiffness matrix for our full system. Doing that, we get this combined matrix here with AE over L in the front. And then we can apply some boundary conditions and use the equation F equals K over U that we've discussed in class. And we can determine the displacement at each of our nodes, and then for each of our degrees of extra degrees of freedom for our enriched nodes. From that, we see that the XFEM approximation is not a nodal interpolant. So then we can calculate the enrichment displacement approximation using our enrichment displacement equations and then our shape function equations as well. And that gives us the value of 0 for U1 or for U at x1, and then we get the value of U, so our displacement that we had at the beginning for x2, and then we get the same for both x3 and x4 here. So that's the walkthrough of the XFEM hand calculation. Arthur will go on to give you some applications of this method.
A quick example to build on the hand calculations and other parts of the presentation that my teammates have just covered. So I used Abacus to generate this 2D axisymmetric model, which essentially involves a rectangle with a circle embedded in it. But because we're dealing with an axisymmetric model, we're only seeing half of it essentially, or a plane, I guess. But what you should be visualizing is something that looks a bit more like this. So a spherical cavity in a rectangular box. It's just that we're mirrored and simplifying the model for computational efficiency. So I'll be showing you essentially this model, but with two variations. One will be using a tensile force upwards to try and impose stress on the model and generate cracks. And the other will be imposing essentially a pressurization in the cavity represented by the semicircle and trying to generate cracks that way. So there are also some resources that I found useful over the course of this project. So I just put a few links at the bottom in case anyone is interested in following up and looking into this further. But let's jump into Abacus. So you can see the model that I was just telling you about, the rectangle with a semicircle embedded in it. These lines essentially are useful for when I generate the mesh define different mesh densities for the different regions. So for now, they're not actually relevant to the actual model shape or setup, but we will get back to that in a moment. I defined this model to have an isotropic linear elastic material. So you can see the parameters below for the Young's modulus and for Poisson's ratio. But because we're dealing with, we're trying to understand cracks and their formation and propagation, we also need to define a failure condition. So that is why we need these damage conditions. So max PS damage essentially defines the criteria for a crack to initialize and form. So whenever a part of the model is experiencing more than the maximum principal stress, which is 22 megapascals here, a crack will form. Once it forms, it will propagate based on the damage evolution criterion. So essentially, once you have a crack in something, it's going to behave slightly differently compared to if it was an intact whole. So that's why we need to account for how the material changes due to damage. So the law that I'm using is the BK law, standing for Benziger and Canane. It's essentially a power law, which governs the fracture's propagation based on these energies that are shown at the bottom. So another consideration that we need to have in Abacus when dealing with XFEM is because when we're looking at damage evolution, that often leads to issues with convergence, just because there's changes in the material properties. So we have to define this viscosity coefficient to try and regularize or stabilize the response of the model during the damage condition and get it to a point where it can converge reasonably. So that is the material that I used. And let's go to this. So besides all the default parameters that you might want to output, there are two in particular that I want to point out that I had to output in Abacus. So fill SM is a signed distance function which describes the surface of the crack using the level set method. And we need to output this because otherwise Abacus doesn't really show the crack in the results properly. So that's why we need to have fill SM output. But more importantly is status XFEM, because we're dealing with the XFEM method. So evidently this is important. So status FEM essentially is a variable that gives the status of those enriched elements that are involved in the crack. So if it's if the status is 0, the element is undamaged. If the status is 1, the element is completely cut through by the crack. And essentially, this value can vary from 0 to 1, depending on if it's undamaged 0 or if it's entirely cut through 1. So that's a variable that I had to output in particular. Here we go. So I've been talking about the crack for a few minutes. So let's go into that very quickly. So you notice that I defined a region, which is this red region, the entire model, for the crack to propagate and initiate in, but I didn't actually define the location of the crack. And the main reason is that I'm trying to see how the crack initiates to start with. So I'm not starting with a crack in the model itself. So we'll just see how that crack will form in the model. So that's why there's no crack location defined in this model at the moment. So in terms of the steps, you see that there's an initial condition and then a static load that I'll impose. So I defined a maximum number of increments of 100,000 with a increment size of as low as 10 to the negative 9, because we need a small enough increment size in order to properly account for the deformation in the model. So moving on to the mesh, like I was telling you earlier, there are different regions where I had different mesh densities. So you can see that the central region has a denser mesh compared to the outlying regions, because that's where we expect the crack to propagate, initiate and propagate. So that's why I generated a denser mesh in the center, but a coarser mesh because we're not as interested in those regions relatively, since we don't expect cracks to form there. So these are all standard quadrilateral elements, and yeah. So moving on to the load. So in practice, I don't have to define a load in this variation because I could do that all in the boundary conditions. We can do it over here, actually. So I imposed two boundary conditions and one displacement condition, essentially. So you can see, for example, over here, I defined that this edge could not move in the x direction. It can move in the y direction in response to displacement, but it can't move in the x direction. Similarly, I fixed the bottom of the model to be unable to move in the y direction so that it's fixed even though we're trying to pull it upwards. Finally, there's the displacement condition. So I imposed a displacement of 0.001 meters upwards in the U2 direction, essentially, in the y direction. So that's what you're seeing with the red arrows at the top. So that is the model itself. So once I ran that model, I got something that looked like this. So we have the contours. So I'll run this once so everyone can have an idea what it looks like to start with. Right. So if we zoom in, essentially what you're seeing is, to start with, the model is stretched upwards vertically. So it's stretching, and then a crack initiates. You can see the crack tip where the where the stress is the greatest as the crack initiates and propagates. So you notice that the crack is in between two elements, essentially, in between in one element. Sorry, it's cutting through the element itself. So that is the power of the XFEM method. We don't have to refine the mesh around the crack in order to generate this model, or to account for the deformation. We can just cut it right through with those enrichment by relying on those enrichment functions. So if we go and look at the status XFEM variable that I was telling you about, you can see that as the model deforms and a crack initiates, you slowly get a higher and higher status XFEM until it breaks and you go to 1, essentially. So that is what we're seeing with this model over here. So now moving on to the variation that I was telling you about with the pressurized cavity. Let's have a quick look at the boundary conditions. So the left side and the bottom are still the same, but there is a slightly different condition for the other boundaries. So I essentially imposed similar boundary conditions for the right side and the top. So the left and right have the same boundary conditions, and the top and bottom have the same boundary conditions. And then I impose a load on the boundary, which is represented by the semicircle. So it's a uniform deformation, pressure deformation, with a magnitude of 2 to the 8, 2 times 10 to the 8. So that essentially corresponds to 200 megapascal, because of it's in Newton per meter squared in abacus. So that's 200 megapascal. It's a bit of a big number, but just for demonstration purposes, it looks clearer in this regard. So I imposed this pressure on the air so that I can propagate and initiate cracks in the model. So you'll see that the model looks quite a bit different. You can see just from this step here. But let's look at the animation again. So you're seeing cracks initiate, propagate, and then eventually it will hit the boundary. So in practice, if you're trying to model these fractures, you would need to have a bigger model. But for the sake of simplicity in this demonstration, I'm just using the same dimensions for the model, just so we don't have to look at an entirely different model. But you can see that even in the middle, you have like even these smaller cracks that are going within the elements. But eventually, the deformation localizes in these larger fractures. And these smaller fractures do not grow quite as quickly as those larger fractures. So if we look at status FEM for a moment, you can see again, as the fracture propagates, you get larger and larger status essentially. So going from 0 to 1 as the crack forms and breaks apart those elements. So that's what we're seeing with status FEM as well.
Some example applications of the extended finite element method that we found in the literature include what we've already discussed in crack and fracture propagation, which also extends to the three-dimensional case. We've shown that this method is exceptional at modeling dislocations in materials, but is also effective at creating simulations for thermal optimization. Perhaps more interestingly, XFEM can be used for mimicking biologic materials. We can mimic the properties of teeth, bone, enamel, dentin, among others. And of course, we're able to model the properties of more common materials like rocks, steel, aluminum, among other more common materials. This concludes our presentation on the extended finite element method, and we thank you for your attention.